Thank you, everybody, for joining today, and welcome to our webinar on the state of ground stations as part of the SmallSat 2021 conference. We're excited to be here today virtually, and we look forward to seeing all of you next year in person in Logan. Just to note, this session is being recorded, and that recording will be available after the webinar ends. The webinar today will begin with a little bit about RBC Signals, and followed by a presentation by our CEO, Christopher Richins, who will talk about the state of ground stations, and followed up by our President and COO, Ron Faith, talking about updates in the cloud and other topics. Finally, we'll conclude with Q&A. And so for Q&A, as you listen to the webinar, if you have questions, there is a box that you can drop those questions into, and once the presentation is concluded, we will address those questions. So just a little bit about RBC Signals. We are a global space communications provider serving satellite operators in GEO, LEO, and MEO with an improved model for the delivery and processing of data from satellites on orbit. The company's worldwide network includes both company-owned and partner-owned antennas, capitalizing on the sharing economy model for best-in-class services offering affordability, flexibility, and low latency. So without further ado, I will turn it over to RBC Signals CEO Christopher Richins to talk about the state of ground stations. Christopher.
Thanks, Sean. I'm looking forward to our chat today. Just as a bit of context, I want to let the audience know that the pieces that I'm going to be speaking to today are intended for people who may not have in-depth knowledge of ground stations and ground station services. And it's really to the people that are just coming in and wondering, what do we need to do to be able to communicate with our satellite? And we find every year as we are working with customers that this is a topic that that's timely and something I hope there's something in here for everybody as we go through. So with that, let's go ahead and go to the next slide. Okay, so what we're going to talk about today, first, planning for success. So I want to go over a few things that are going to really help a new satellite operator think about how to structure their communications and really set themselves up for success in their space mission. Then we'll go through some of the things, the practical elements that occur during the launch and operations phase. And then we'll turn the time over to Ron to discuss how to future-proof your strategy and take advantage of some of the things that are new technological developments that are coming into the industry. So my name is Christopher Richins. I'm the founder and CEO of RBC Signals. My background is engineering based. So I have an undergrad degree in electrical engineering, a master's degree in astronautics, and really have spent almost the last 20 years working in the space industry, dealing with communications, both with launch vehicles and with satellites, and how to get those signals back to the users that need them. We'll have Ron introduce himself as he starts his portion of the presentation later today. So to begin with, I just want to give a high-level overview of the elements of a space mission. And these are the parts that really, regardless of what the mission of your spacecraft is, that are going to be components of the mission that you're operating. So every satellite that gets into space has to be launched. That's something that we understand. But this thing in the middle, this graphic that says satellite TT&C, may not be familiar to everybody. So what that references is telemetry, tracking, and control. That is the acronym TT&C. So when the satellite is flying, it may have a mission and a payload that it is trying to perform. So that payload might be taking pictures, it might be a camera. The payload could be a radar for synthetic aperture radar. It could be an antenna for listening and detecting signals or communication. Regardless of what the payload or purpose of the satellite is, the satellite itself has some common features that need to be operated and maintained as the satellite is flying. And so that's where the telemetry, tracking, and control elements of the satellite mission come in. So the satellite itself consists of a bus, which is the mechanical structure, and the computer and communication systems that kind of support the payload. So TT&C information are basically, it's that information that's required to keep the satellite healthy and operating to support the operations of the payload. And so you'll have things like maybe temperature, battery voltages, orientation, location data, and all of these things help satellite operators understand the relative health of the bus or of the satellite itself. And then the payload is going to be doing whatever it does, but there needs to be some way of communicating that payload information that is being generated or captured by that payload instrument and delivering that back down to the users. As we know, space is a tough place. You can't have a long extension cord. So all of that happens via wireless communication. So both the command and control of the satellite to command it to do different things, as well as to receive that data back from the payload, all is done via wireless communication or RF communication, where RF means radio frequency. And so you may have RF engineers as part of your team that are going to help you with the fundamental elements of that communication. And generally speaking, the way that that information returns to Earth is via the ground segment. So the things that you see within the box below, where you have a picture of a satellite dish. That satellite dish is also called an antenna, and a ground station can refer to the antenna itself, but generally refers to all of the systems that are providing support and communication to that satellite as it's flying in space from the ground. So we have a satellite dish, and then you're going to have the computers and servers and other communication equipment, the radios, et cetera, that are going to enable that wireless communication to happen with the satellite. And then once the payload data is received from that satellite dish, from the satellite, you're going to have some manner of processing that happens to prepare that data for dissemination to its final user, whether that's an image data or some other information that's used. And so all of that processing has to happen somewhere on the ground, whether that's local to where the antenna is, where we would call that edge computing, and Ron will talk more about that later, or it could be backhauled to the cloud and processed at a data center back at a customer facility, or even at the satellite operator, or in an Amazon, Azure, Google Cloud, or other cloud provider. So at a high level, these are the key elements of a space mission. And really what we're going to be talking about today are how can we really understand the communication requirements both for TT&C, so telemetry, tracking, and control, and payload data dissemination from the rocket, or excuse me, from the spacecraft. And so that will require both uplinks from the ground to space for the command and control of the satellite, and downlinks from the satellite back down to users on Earth. So with that overview, let's go ahead and talk about some high-level things that we can do as satellite operators to ensure mission success. And so one of the first things that I want to talk about today is the lost art, I call it, of systems engineering. Back in the early days of space, systems engineering was a critical function that was really baked into the processes that went into building a satellite and preparing it for launch. So when these were government-only operations, there would be huge organizations dedicated to making sure that end-to-end, that the systems were going to integrate well with another, the systems on the satellite and the systems all the way through to delivering data to the customer were all working together. As we've moved into a more commercially driven space industry, some things are, sometimes this discipline of systems engineering has been less of a focus, and I'm really advocating for a return to systems engineering. We'll talk a little bit more about what that means. But basically, it means that we start from the customer's needs. What are we supposed to be delivering to the customer, and really understanding their requirements. And so all of the requirements of the satellite and of the communication system should really be able to be tied directly back to the requirements of that end customer and what they are willing to pay for. So that way you prevent yourself from delivering more or less than the customer needs, and you're able to be really efficient with your designs. The warning here is if you don't do a requirements-based systems engineering job, you may either end up really overbuilding your spacecraft and making it cost more than it should, or you could get a satellite that's up in space but not able to meet the requirements of the customer. So really understanding what the customer needs and how those requirements flow back to the way that the satellite is built and operated are going to be important. And so having that systems engineering function really helps. The second bullet talks about being commercially minded. And so what does that mean? It means, are we building things into our system that people are willing to pay for? So again, back in the days of having a government system, being budget conscious wasn't always the highest priority. In fact, a lot of times failure is not an option was really the mantra of how these systems needed to work. And for some life critical systems, that's exactly the way we ought to be thinking about it. But for a commercial system, we really should be thinking about what is the value that a customer is willing to pay for. So as you're establishing requirements for your system, make sure that you're doing it in a way that is commercially feasible and is tied back to what the customer wants. The third point I'll make on systems engineering is systems engineering should be holistic. One of the things that we see is that in many companies, rather than having a systems engineering function that is tying all of these things together, we will have subject matter experts in the firm where you might have a structures expert and a communication expert and a power systems expert and a software expert, but they kind of are doing their development in a silo. And when they do that, they may be making trades on different aspects of the system that may not be what is in the best interest of the spacecraft mission as a whole. So you might, for example, have a power engineer that wants to have a smaller battery to save mass for his allocation. But what could end up happening then is there's not enough power available to operate the payload for as much data capturing as is needed, or there's enough mission battery power to be able to capture the data, but then we can't operate the transmitter as much as we need to be able to get the information from the spacecraft down to the users. So when we take a holistic approach, it really means that we're taking a cross-disciplinary approach to systems engineering that, again, ties everything back from the customer's requirements to what they're willing to pay, to what our budgets need to be, and to how all of that works together. And so finally, these things are done on an iterative basis. So typically, again, back in the old days, you would have a series of design reviews that would ensure that all of the customer's requirements are being met in a commercially minded way, and that all of the various subsystems are operating together in a seamless manner. And so you might have a PDR, which is a preliminary design review, and that would be an opportunity for everybody to provide input from all of the different disciplines. Then you would go to a CDR, a critical design review, and then you would go to build. And so I really highly recommend that systems engineering approach with these reviews be built into every spacecraft's design. And that will help all of the functions to work together well and to ensure that you're able to meet your customers' requirements on budget and to be able to really expand your business. Okay, so once you've got that systems engineering approach, the next thing that you really need to be thinking about right at those early stages of your spacecraft design and development is the regulatory piece, and where are you going to get your licenses from? So we recommend that this process start right at the very earliest stages of your mission operation. excuse me, not your mission operation, your mission design. So just as you're thinking about your company or thinking about what your customer is going to need, be thinking about what licenses do you need to be able to operate. So that might include licenses for spectrum. If you're going to have a radio and communicate with your satellite, which every satellite will, then you're going to need to have a license to operate that satellite or use that spectrum. Even we'll talk a little bit about optical in the future, and there may be requirements to even license that. So things to look at. You're going to need a launch license. You're going to need a spacecraft operating license. And sometimes the operating license and the launch license can go together, but in some countries they don't. And so you may have to separately license your spectrum, your launch, and your satellite operations. And so you need to be checking with your local regulatory bodies on what requirements need to be met. So as you are going through the process of filing for your various launch, operating, spectrum, whatever you need, as you're filing those different licenses, it's really critical that you are consistent with the information that you're putting into these license applications. And that can be a challenge, especially if some elements of the design are changing over time. And so one of the things that we want to do is make sure that the information is consistent across all of those different filing bodies. So as we continue to work through this process, it can be really important to get help in those filings, because unfortunately, the bureaucratic bodies that are responsible for granting these licenses, they may not be very user-friendly, and you may not get very good feedback from them for why your license may or may not have been granted. And you can get rejections, and sometimes these processes can take many months. In fact, we recommend that from a spectrum licensing perspective, the absolute minimum that we recommend before you file for your spectrum licenses is 9 months. And really, it should be 18 months or more before you intend to launch that you're making those spectrum filings. And that will allow you to make sure that you have plenty of time to deal with the frequency coordination process. So one of the things that we see often as customers come to us is a real lack of experience with this spectrum licensing process. So I just want to take a couple of minutes and talk about a few of the key elements of that, because as you do that, you'll find why it's going to take such a long time. So most spacecraft operators that are bringing data down on a regular basis from space may want to operate from more than one ground station, which may mean that you have to get a license to operate in more than one country. And as soon as you are operating in more than one country, then you may have to start dealing with the ITU. And so the ITU, the International Telecommunications Union, I believe is the acronym there, but the ITU is a group that really helps facilitate global satellite communications and spectrum, so that spacecraft that are operated in space that are inherently flying over every country or almost every country as they go about their missions are able to conduct those operations in a way that doesn't interfere with either other spacecraft or other national priorities for those countries. And so filing notifications with the ITU is important. And depending on the frequency bands that you are operating in, the spectrum that you want to use may be spectrum that has to be pre-coordinated, and you actually have to be granted that license from the ITU to be able to use it. Or it may be uncoordinated spectrum that has to be coordinated with other, with other potential users of that system. So of that spectrum. So as you work with the ITU, you will find out what your regulatory requirements are, what your licensing requirements are, and but that process takes a long time. And so the reason that we say it's important to get help is because that will help you move more quickly, number one. Number two, it will help you be, it'll actually help save cost so that you're saving on filing fees and things down the road. And lastly, it'll save you from delays. We have had customers who have unfortunately been removed from launches and had to miss their launch opportunities because the licensing process hadn't been followed. One other thing that I will say is, in addition to the spectrum, the launch and operation licenses, one other area of license that can sometimes be a challenge, at least in the United States, or something to be aware of, if not a challenge, is if you're flying cameras on board your spacecraft, you may have to license those cameras. And so NOAA in the United States is responsible for granting those licenses. And so you'll have things like data protection plans that need to be filed. And so all of these things actually are part of, should be part of that entire design and build process. And what we find is a lot of our customers are so focused on the really cool technological parts or focused on the business parts of it that they really aren't taking time to look at the that licensing element. So start early, know which licenses you need, be consistent with the information that you provide regulators across the different filing applications, and get help where you need it. Okay, so the next topic that I want to talk about is, in order to build for success, is testing. So just like from the regulatory standpoint where you want to start early, you want to start early on testing and thinking about how are you going to test your spacecraft to make sure that it's working before it gets on orbit. And there are a lot of different functions within a spacecraft, and you want to be able to have a plan on how those things are going to be tested. And to the extent possible, you want to build in the ability to test it along the way. And sometimes that means having engineering models or a flat sat that you have running beside your spacecraft before it launches, so that you have all of the systems in an identical configuration, so that after your spacecraft is launched, you've got your engineering model sitting right next to it, right next to you in the lab. So if you're seeing unexplained behavior of your spacecraft in space, you can replicate those things on the ground. From a software perspective, you can be making sure that you've got quality testing baked in along the way as you go. The last acronym at the bottom, TWYF, FWYT, test what you fly, fly what you test. This is especially important in communications links. So one of the things that we see where our customers are having problems is they make an assumption that because they are buying a radio off the shelf, that it's automatically going to be compatible with any ground station that they choose to use. Especially in this day and age of ground stations as a service, where you might use other people's antennas to be able to facilitate your communication, and we'll talk more about that in a few minutes. There can be an assumption that every radio just works with every ground station. And this actually should be tested before you launch. And that enables you to ensure that that communication is going to happen the way that you expect it to. We have had customers come to us saying, hey, we launched our satellite. We thought it was going to work. It doesn't work. We need you to help us now. And so we would do everything we can, but sometimes there's nothing you can do if you can't communicate with your spacecraft and you can't recover it. So testing before you launch and testing the exact configurations and exact modes and exact software is absolutely critical. Sometimes we see customers thinking that, oh, there's a few months between when my spacecraft has to ship to go to the launch integration and when it launches. And they will sometimes think, okay, that's time that we'll use to do software development to kind of fine tune how we'll operate the spacecraft or how communications will run. This can be a significant challenge, because if you haven't tested what you're going to fly, if you're not flying what you tested, then you haven't really done testing, and this can really be a problem. So start early, bake it in, have that plan, test what you fly and fly what you test, and you'll avoid a lot of the heartache that we can sometimes see. Okay, so with that, I want to talk a little bit about this ground station as a service that I mentioned briefly before. So when a satellite is launched into orbit, depending on the orbit that it goes into, assuming that you're going into a low Earth orbit, you are going to be constantly in motion relative to a satellite dish or a ground station on the ground. And depending on which orbit you're in, you may only see that satellite above your ground station a few times a day. And in fact, for a lot of the popular orbits, like a sun synchronous orbit, a polar orbit, if you're in a mid-latitude, say in the United States or in Europe, in Asia, you may only see a satellite fly overhead 2 or 3 times a day, meaning you might get 30 minutes of communication time. And for 23.5 hours a day, you have no ability to communicate with that satellite from that ground station. So if you don't have multiple ground stations around the world, you may be limited in terms of the volume of data that you're able to bring back, the timeliness with which you're able to bring data back. That's also called latency, how much time from the time data is created to the time that it's delivered to users. And you may also be limited in terms of your ability to command and control the spacecraft, to task it to do different things. And so a way to avoid that or to mitigate some of those challenges is to have a global network of ground stations. Now, again, this should be requirements-based and requirements-driven based on what your customers actually need and the needs of the technologies within your satellite bus. But you really should think about and plan for how much data and when it needs to be delivered to your users. And so one way to solve some of the challenges that that global ground station network can present is to actually use a ground station as a service provider. And there are several out there in the world. RBC Signals is one of them. And I'll talk a little bit today about how you can use a ground station network as a service provider to be able to save the cost, complexity, and the challenges associated with maintaining your own global ground station network, which would be otherwise required if you weren't able to use infrastructure as a service. So let me say a few words here about the service that RBC Signals can provide. So first of all, the map that you see here is a map of our antenna ground station locations. So this is a mix of stations that are owned by RBC Signals and also stations that are owned by our partners. Very early on in the history of RBC Signals, we recognized that we would have partners that were only using part of the capacity of their antennas. And so we make it possible for ground station owners to contribute their unused capacity to the RBC Signals ground station network so that we can then bundle that together and provide that capacity to our customers. And then we're able to share revenue to be able to make that worth the while of the ground station operator. And Ron will talk a little bit more about how to join our network if that's something, if you're a ground station owner and think that might be something that you're interested in. But we have antennas in our network that cover the full spectrum of satellite operations, from VHF, UHF, S, C, X band, KU band, KA band, even optical is in our network. And so to the extent that you need ground stations that support those frequencies, we have the antennas already available in the field today that you would be able to use to be able to meet your communications requirements. We'll talk a little bit more about how to use our system, but scheduling antennas with RBC Signals is as simple as a very straightforward API. An API means that it's a computer-to-computer interface, that you don't have to sit there and click a box and go through a web interface or some other software tool every time you want to plan a ground station network, but you can automate the scheduling and delivery of your data, scheduling of passes and delivery of your data directly through our systems. And by having this kind of a shared infrastructure model, you're able to have the benefit of a full global communication network with antennas all over the world without having to bear the cost of deployment, operations, maintenance, modernization, and licensing and the regulatory hurdles that you would have to otherwise jump through. Okay, we have two primary service levels when we talk about antennas within the network. Some customers require dedicated antenna systems, whether for security reasons or because they have enough satellites in their constellation that they can fully utilize the capacity of an antenna. And we call that our core ground station assets. So a core antenna is an antenna that's guaranteed for a customer. They're able to use that as if they owned it. Basically, they have unlimited use for a flat monthly fee. It can be placed anywhere in the world where that's needed. And it really provides that base level of support to support a mission where you want to have that guaranteed capacity. And then we can augment that with what we call our network level of service, which is our shared antenna time, where you're able to use that global partner network. You can schedule those up to 48 hours in advance, and you're able to lock that in up to 30 minutes ahead of your satellite pass. All of these are subscription-based services where from a core antenna perspective, you're paying one flat fee for unlimited use. On the network side, you're paying for either a number of passes per month, a number of minutes per month, really paying as you go as you use different services. So it's a really flexible model that allows you to use exactly what you need and to be able to scale your operations as you add satellites to your constellation. So when you come to RBC Signals to use the service, it's actually a pretty simple onboarding experience. So the first thing we're going to do is we're going to gather the requirements for operating with your spacecraft. We're going to be looking at the orbit that your spacecraft is in, how many spacecraft there are, what frequency bands are you operating in, are you transmitting from the ground station, are you doing command and control, or are you just downlinking data? We'll look at the modulation and coding schemes that you're using. We'll look at the polarizations, and then we'll look at the overall volume of service that you want. Do you just want one pass per day? Do you want a few passes a month? Or do you need to have one pass per orbit of your spacecraft? Regardless of the volume, we have capacity to be able to serve those needs. And so once we understand what you need, then we can go to our network and evaluate whether we have antennas in the network or whether we need to build additional capacity to be able to support your mission. So we'll select and certify those antennas. And then all ground stations need to be licensed for the satellites that they're supporting. So just like you'll have to get licenses for your spacecraft, we also have to make sure that the ground stations are licensed. So very early on, as soon as we understand your requirements, one of our first steps is to go out and get those regulatory boxes checked. And that might include doing pre-coordination with other satellite operators who may be trying to use that same spectrum in the same locations. Then finally, once we've done that, we will make sure that we have the systems and interfaces lined up. So make sure that you understand the API and how to use that. And we have a sandbox environment that allows you to test out those APIs before we get to launch. And then we'll make sure that the data delivery flow systems are set up so that once the data comes down, you're able to very quickly deliver it back to your data center, mission operations center, or users. The sites then are prepared and we're waiting and ready for launch. So when it comes time to start operating your spacecraft in orbit, you'll be interfacing via the API with the ROS system, or our RBC operating support system. And at a high level, what it's doing is it's got a database of the full capacity of our global ground station network. And it's constantly using the location of your spacecraft via the TLE, or the two-line elements that describe your spacecraft's orbit. It's constantly calculating the visibility windows to all of the ground stations in our network that are available for your use. And as you request times to communicate with your spacecraft, it's checking that database, ensuring that those times are available, scheduling it, and then we send that command to track your spacecraft out to the ground station. That ground station responds, accepts that ground station pass, and then prepares the antenna to track the satellite. So then as the satellite rises over the horizon, the ground station is already pre-configured with all of the frequencies, modulation and coding schemes, and all of the data pipes are set up to be able to deliver that data back to you, the user. And so as the satellite is being tracked across the sky, that data is then either being stored for processing and forwarding at the end of the pass, or it's being streamed in real time back to the Satellite Mission Control Center. After the pass, we are able to send you a post-pass report that described all of the key characteristics about that pass and the quality of that communication. And then we're able to handle all of the billing and other services as part of that system. So really, all of that's happening in the background. And for the user, it's as simple as telling us when you want to use the system and getting it scheduled through the API. All right, so with that, I really have appreciated the opportunity to present that high-level overview of some of the lessons that we've learned through our experience at RBC Signals. And now I'll turn the time over to Ron Faith, our president and COO, who will introduce himself and then talk about some of the things that we can do to future-proof our missions to be able to prepare for what's next in satellite.
Thank you, Christopher. And I'd like to thank everybody again for participating in our session today. So first of all, I'm Ron Faith. I am the president and chief operating officer of RBC Signals. I'm also an electrical engineer by background. And so I got my master's in electrical engineering from the University of Washington and got my engineering and philosophy double major from Dartmouth. I have worked over the years in enterprise data and mobile telecom data, working for both large wireless carriers as well as DoD and intelligence community customers. And so very excited about some of the things we're seeing. I was joking with Christopher before the session that while he got to talk about all the steak, I get to talk about the sizzle. And so we see lots of fabulous trends going forward. One of the advantages for RBC Signals, because we have so many customers with varied backgrounds, whether they be commercial operators or whether they be government satellite operators, and then also a range of applications going from Earth observation to IoT to straight up data comms. As a result, we see all sorts of requirements of new and exciting things that are going on in space and what those implications are for ground solutions in being able to support them. Because remember, every satellite that goes up, and we're now getting thousands of small satellites going up, has to be able to talk to the ground in order to provide its value. And that fundamentally, most of the value that's going up nowadays are in the form of data services. And so as a result, we're seeing a real shift towards data-centric architectures going forward. We're going to talk a little bit about that today as well. So the first thing is a real break with tradition that we see going on. So traditionally, governments are the ones who put up satellites, and therefore governments were the ones that built their ground systems, and that there was a one-to-one relationship between a mission and its ground station, a satellite and its ground station. And we're seeing a real shift in that. So first of all, the move to small satellites means a greater move to constellations, whether those are large constellations or small constellations, or quite frankly, some satellites just flying in formation together, doing interesting things, looking for Earth deformation, for example, and things of that nature. So as a result, there really is this need to be more cost effective with ground station resources. And that means making it so a ground station can support not just one mission and one satellite, but be multi-mission and multi-tenant in nature. And so one of the key places that we've learned a lot of lessons from over the years is how the public clouds tackled this similar challenge that we saw in the data center world for the longest time. So enterprises used to have their own data centers, their own dedicated servers for their own workloads, et cetera. And what we saw over time, in order to get both cost efficiencies and scale and higher reliability, that there was this dramatic movement towards virtualization of the workloads on the servers, so that could be a server could be more robust in handling different workloads on it, as well as being distributed in the nature of those workloads across servers. And then finally, the ability to have those workloads happen across data centers, or in the public clouds, and in the case for governments, the gov clouds. And so what we're seeing happen in ground stations is very similar and analogous to what we saw happen with the adoption of the public cloud. And so this need to be multi-tenant, multimodal, multi-mission, and the ability to have great flexibility at the ground station in terms of how quickly you can configure a ground station for a given customer. And that may be from pass to pass, from minute to minute, that's going on. And we see that across our customers today. We have multiple customers sharing the same ground station resources, but having really good isolation from one another from a data security standpoint and from a resource and processing standpoint. And that's what goes into this next point of software-defined ground stations. We've seen a real shift here to where a lot of what we used to see on ground stations was dedicated hardware, dedicated systems, custom-built systems. And so now what we're seeing is, whether it's software-defined radios or the processing that's going on at the ground station, et cetera, a much more highly configurable environment that is software-defined, that, quite frankly, a customer comes in with us, we set up their profiles and configurations across the ground stations that they're licensed to work for and that are compatible with their technical requirements. And then on the fly, from pass to pass, we're able to build up, whether it's in a software container or what have you, the ability to support that pass for that customer, do it via software-defined radio, bring that data down, process that data at the ground station if need be, and then get those data products, whether in real time or in batch, to the end customer, depending on what their business need is. And that's a dramatic shift. The also big dramatic shift that we're seeing is in the area of cybersecurity. So we obviously follow all the NIST cybersecurity requirements, especially given that we have government customers. One of the things that's coming down the road is CMMC requirements. There are also new initiatives for NIST for creating profiles specific to ground stations and the cybersecurity associated with that. And we participate in those groups associated with those things. And so, so one of the things you should be asking and talking with your ground station providers about is cybersecurity. And it's not one size fits all, right? But there are some base block and tackling that needs to happen, because increasingly valuable and sensitive information is flowing through these ground stations, and the ability to both command and control the satellites and to be able to handle encrypted traffic and be able to configure the ground stations for passes all needs to be under a good risk management framework, a la a cybersecurity framework that will work for you, while not being too stringent for you to not be able to do what you need to do. Okay, fortunately, the cloud folks, especially the big public clouds, have a ton of experience in cybersecurity requirements, and we're all benefiting from some of those by adopting a lot of those practices. So the other major trend that we're seeing is that as more satellites are going up, the capabilities of these satellites are going up dramatically. And so it wasn't that long ago that the DoD used to refer to SmallSats as crapsats, right? A little over a decade ago. Nobody calls them that today. The sensors that are going onto these satellites, some of the computing horsepower that's going onto these satellites, and the sheer amount of data that needs to be moved from space down to the ground is requiring increasing data rates. So there's different ways to achieve those. One is, as they move up into higher frequencies, again, SNX is a lot of where our bread and butter is, and we see every day, especially in Earth observation, X-band downlinks and things of that nature. But we're also increasingly seeing Ka and Ku requirements coming into the to the marketplace. And as you go up in frequency, it means you can go up in data rates, and it's not without its challenges, but it does mean that you can handle higher data rates and then higher data volumes. The other things that you need to be thinking about in that area as well is look at your link budgets, and do you need more ground stations to cover more passes to be able to get more data to the ground more quickly, right? And that's where having a global ground station network where you might be able to use an array of X-band downlink capabilities in multiple geographies so that you can rapidly get this data down ends up being critically important. We are also seeing advances in phased array technology. So again, this again helps in the notion of multi beams, being able to support multiple satellites at the same time and therefore be able to get more data down at the same time. The other thing that we're seeing increased interest in dramatically, and we've deployed our first optical ground station, and so and we've got others in the works here, and we're seeing increasingly the need for optical because one, it's a little less stringent on the regulatory front for now. We'll see what happens in the future. But then also you get much higher data rates. And so where we believe you're going to see a lot of headway made in optical is in inter-satellite links first, because of free space and the ability to deal with it. You still have lots of challenges on pointing requirements and things of that nature in those areas. And then we'll eventually see more and more adoption of optical downlink. But because of some of the challenge with atmospheric scattering and weather and things of that nature, that's almost always going to need to be coupled with some RF for resiliency standpoint. And so we look forward to continued progress in optical. We're very much looking forward to both phased array and optical, as well as K and KU, that as more and more demand happens, we'll see the ability to have price points come down associated with volume and have that come into more and more commercial oriented applications as opposed to just government related domains where we see a lot of these things today. Finally, I wanted to talk a little bit about what we're seeing in data-centric architectures. And so one of the things that's happening is this move towards a distributed compute architecture. And so where, so not only is there a large amount of processing going on at the data center, which is increasingly becoming the cloud, quite frankly. So we're seeing more and more workloads move to AWS, Microsoft Azure, and other clouds, quite frankly, where there's big, not only a lot of compute resources that are elastic in nature, where you can expand and contract and control budget a little better associated with those data loads. And you can also store securely very large amounts of data, okay? But we're also seeing advanced data services around AI and machine learning and data lakes and data processing going on in the clouds as well. So as a result, some of our partners, such as AWS, have also put in place ground stations as a service offerings in conjunction with their data centers. So AWS is a partner of ours. Their antennas are available in our network, and we work with them very closely. But what we find for most customers is that they need a hybrid solution, that some of their requirements may need a more dedicated antenna, for example, in an Arctic location, while some of their other needs might be how quickly can I get an X-band downlink to an AWS ground station so I can quickly process that data. And we're able to collaborate and work to provide that total solution. We're also going to see something similar from Microsoft as they head towards general availability in the area as well, which is very exciting. At the same time that that's going on there's increased need for what we have traditionally called edge computing, which is part of a distributed compute architecture. And so there's more and more demand for being able to do compute on board on the satellite. And we're going to see some advances in those areas, but that's going to take some time as because of the amount of compute resources and what's available on the sats, et cetera. But we're going to see more and more adoption of that, and we're excited about that. but then also where the terrestrial edge meets. So where does the data first land on the ground? And that's at the ground station. And so the ability to do very quick processing and be able to turn that around in advanced data products at the ground station, but also use those as an extension of the cloud. So if you're an AWS customer or an Azure customer for using your backend, and you want to be able to have your ground station be an extension of that cloud from a governance and management standpoint, or you may want to use AWS Outposts or Azure Stack at that ground station, we provide that as part of a solution. And so we're very excited for what we're seeing going forward here. Not only are we excited about the advances that we're seeing, we're excited about the applications that are going on and just the radical new requirements we see almost every day. We're seeing small sats everywhere. So when we first saw small sats, it was maybe just in LEO, in low Earth orbit. We're now seeing mid-Earth orbit, MEO, and GEO applications associated with small sats in very unique orbits and unique data processing needs as well associated with some of their missions. And so we think there are very exciting days ahead associated with that. So finally, we know every year at SmallSat, there's a number of folks that have ground stations, and we always get asked the questions, how can I add my ground station to the RBC Global Ground Station Network? It's pretty straightforward. So first of all, we have a standard contract with everyone associated with a rev share on the utilization of your unused capacity. So first of all, you tell us what extra capacity you have on your ground station, what your technical requirements you are in terms of your capabilities, what frequency bands, your size of your antennas, what radios you have, et cetera. We put that into our catalog of capabilities, and then we constantly have customers. We're doing RFP responses all the time. And then what we try to do is do some matchmaking between what the customer's requirements are and antennas that we have in our network, which could include yours. And then we let the customers select what is it that they want to be able to utilize as part of a total solution. And most of the times it's a hybrid solution where they might be using some of our antennas, but they're also using partner antennas where they've got a more dedicated antenna resource that they're utilizing, but then they're also wanting to use the network for more expanded utilization as they have periodic needs that increase in data volumes for what they need. So what we encourage you to do is come to the website, www.rbcsignals.com, enter the contact page for us with your information. We will circle back with you. You will then get a form from us that basically asks for all of your ground station details and information. We'll then work with you. We'll also send you the base contract for things like that and work with you. Just to give you an idea, we just signed up 2 more ground station partners just in the last week, adding yet again to our global coverage on things, which has over 80 antennas in over 50 locations around the world, providing customers phenomenal reach and capabilities. So with that, we would now like to open up to Q&A for any questions that you might have over the last minutes of the session. Again, we appreciate everybody that's joined today, and we'll let Sean moderate the questions and let us know what you guys are asking and thinking.
Thanks, Ron. Thanks, Christopher, for presenting. So we'll give it people a little bit of time to drop in questions. So again, if you have a question you'd like to ask, there is a Q&A button, and so you just type your question in. I'll see it, and we can forward it on. And just a reminder, this webinar will be recorded and will be up on RBC Signals YouTube channel. And so we have a variety of videos that address the things we've talked about today and lots of other topics related to ground station mission planning, operations, and support. So we'll keep waiting. So far, no questions, but we will hang out here for a little while longer.
Actually, I just saw a question come in. So one question is, do license or requirements for ground stations, are they different from geography to geography? This has to do with a jurisdictional issue and whether you're getting licensed in the US or China or what have you. Christopher, do you want to try to tackle that one?
Sure. So every jurisdiction, every country has a different set of requirements. So yes, and some are easier to work with and have clear, well-defined processes than others. And so it varies widely. I will say that spectrum is one of the most valuable natural resources available to every country. And so many of them safeguard it because of that. And so fortunately, RBC Signals has an incredible network of professionals around the world that allow us to work through the regulatory processes in any country. And sometimes that might include helping them actually define some of those regulatory processes if it's a country that doesn't have highly matured space activity. So yes, every country will have different requirements. Some may require licenses for transmit and receive. Some may only require licenses for transmit only. It really does vary anywhere in the world that you go.
So next question is, what different size antennas do we have in our network? And, you know, can we handle things like cislunar and things of that nature?
So in our network, we have everything from Yagi antennas for VHF communication all the way up to 32-meter dishes, which can absolutely be used for lunar communication. That said, lunar communication is a particular challenge, and I would say that capacity for lunar communication is a challenge anywhere in the world right now. And so if you have lunar missions that you're planning, my recommendation would be to reach out to ground station operators very soon to be able to start accommodating those needs. But yes, we have dishes of all sizes. I would say most of our dishes are probably in the 3.7 to 4.5 meter range. But we do have multiple dishes in the 30+ meter class range.
So I think that's going to conclude our Q&A for today. Christopher, any closing remarks that you'd like to make?
Thanks, Ron. I've really enjoyed being able to speak with you today. I hope that if you have any other questions that you maybe weren't comfortable asking in the group, that you would please reach out to us, www.rbcsignals.com. We would be happy to work with you to review your requirements and really help you ensure your mission success. So thank you, everybody, for being with us today.
Thank you, everyone, and I hope you enjoy the rest of SmallSat, and we look forward to hopefully being with everybody in person next year. Stay safe, stay healthy.
Thanks, everybody. This concludes our presentation.